The year was 1999. Pickup trucks were getting bigger, heavier, and more complicated. Manufacturers were chasing more power, more towing capacity, and more technology. But deep inside Chevrolet's engineering offices, a different idea was taking shape. Nobody knew it at the time, but a humble 5.3-liter V8 was about to become one of the most durable truck engines America had ever seen. Today, you can still find them everywhere. Construction sites, ranches, oil fields, small towns, big cities. Some have 200,000 miles, others have 300,000. A few have crossed 500,000 miles and just keep going. But what almost nobody knows is that the 5.3 Vortec wasn't supposed to become a legend. It wasn't the biggest engine GM built. It wasn't the most powerful. It wasn't even the flagship V8. Yet somehow it outlasted engines that made more power, cost more money, and grabbed all the headlines. So what made Chevrolet's 5.3 Vortec nearly indestructible? The answer starts with a revolution inside General Motors. Back in the early 1990s, GM knew its traditional small block V8 was reaching the end of its life. The old Gen I architecture dated all the way back to 1955. It had powered everything from Corvettes to work trucks, but emission standards were tightening, fuel economy requirements were rising, and customers expected more refinement. The original small block had served admirably for decades. It was legendary in its own right. But technology was advancing, and the competition wasn't standing still. Ford was developing modular V8 engines. Dodge was refining their Magnum series. Import brands were making inroads into the truck market with surprisingly capable engines. GM needed a clean sheet design. The result was the LS family. When engineers began developing what would become the Gen 3 small block, they focused on something many competitors ignored: structural strength. The development team faced enormous pressure. They were replacing an icon. The original small block had built GM's reputation. Any successor needed to honor that legacy while meeting modern demands. They started with the foundation. The engine block was built with deep skirt construction. Instead of stopping near the crankshaft centerline like older V8s, the block extended much lower. 6-bolt main bearing caps secured the crankshaft. 4 vertical bolts were joined by 2 cross bolts that locked everything together. It looked almost excessive, but there was a reason. Truck engines live brutal lives. They spend hours towing trailers, climbing grades, idling on job sites, and hauling loads in extreme temperatures. The crankshaft experiences tremendous stress. Every time a piston fires, forces try to flex and twist the crankshaft. Over hundreds of thousands of cycles, weak points fail. GM wanted an engine that could survive abuse for decades. The engineers ran simulation after simulation. They tested prototype blocks until they cracked. They measured deflection under load. They studied failure modes from earlier engines. Every lesson learned went into the new design. The first truck version arrived in 1999. Known internally as the LM7, the engine displaced 325 cubic inches, or 5.3 liters. It used a 3.78-inch bore and a 3.62-inch stroke. Compression ratio was a modest 9.51. Output was rated at 270 horsepower and 315 pound-feet of torque. Those numbers weren't revolutionary. Ford's Triton V8s and Dodge's Magnum engines produced similar power. Some competitors were already pushing past 300 horsepower in their truck engines. Automotive journalists didn't write glowing headlines about the 5.3's power figures, but power wasn't the real story. Durability was. The LM7 featured a cast iron block in many truck applications. Cast iron is heavier than aluminum, but it's incredibly tough. Cylinder walls resisted wear. Main bearing saddles stayed stable under heavy loads. Heat cycles caused less distortion. In other words, it was built like industrial equipment. The material choice was deliberate. Aluminum blocks save weight and improve fuel economy slightly. Marketing departments love advertising weight savings, but cast iron has advantages that matter more in harsh conditions. It dampens vibration better. It handles heat differently. It's more forgiving when things go wrong. Most people don't realize just how conservative the engineering was. Peak power occurred around 5,200 revolutions per minute. The engine rarely needed to spin fast. Mean piston speeds remained relatively low. Internal stresses stayed manageable. Components weren't operating near their limits. Compare that to some high-performance engines that redline at 6,500 or 7,000 revolutions per minute. Higher speeds mean higher stresses. More stress means faster wear. The 5.3 avoided that entire problem by simply not needing extreme RPM to make useful power. That conservative approach would become one of the engine's greatest strengths. But there was a problem. Truck buyers weren't interested in engineering diagrams. They cared about towing, and GM needed the 5.3 to prove itself in the real world. The challenge came quickly. Throughout the early 2000s, Chevrolet Silverados and GMC Sierras, equipped with the 5.3 Vortec, began accumulating staggering mileage. Fleet operators started reporting trucks crossing 200,000 miles with little more than routine maintenance. These weren't pampered vehicles. Fleet trucks get beaten mercilessly, different drivers every week, maintenance schedules sometimes missed, heavy loads, constant stop-and-go driving. If there's a weakness, fleet service exposes it quickly. Then came 300,000, then 400,000. Mechanics noticed something unusual. When engines finally came apart, cylinder bores often still showed factory crosshatch marks. Main bearings looked surprisingly healthy, compression numbers remained strong, wear patterns were minimal, even after years of hard service. One veteran GM technician reportedly joked, "These things wear out the truck before they wear out the engine," and he wasn't entirely wrong. Frames rusted, bodies developed holes, transmissions needed rebuilding, suspension components wore out, but the 5.3 just kept running. Owners found themselves replacing everything around the engine, while the engine itself needed nothing more than oil changes and occasional spark plugs. But durability doesn't happen by accident. One key advantage was the engine's oiling system. Older small block designs sometimes struggled with oil control under extreme conditions. During hard acceleration or when towing up steep grades, oil could slosh away from the pickup. Pressure would drop momentarily. Over time, those moments accumulated into damage. The LS-based 5.3 improved oil flow throughout the engine. Priority main oiling ensured critical crankshaft bearings received lubrication first. That sounds simple, but it's huge. When oil pressure drops, the crankshaft bearings are usually the first components to suffer catastrophic damage. They spin at tremendous speeds under enormous loads. Even a few seconds without proper lubrication can cause scoring, heat buildup, and eventual failure. By feeding the mains first, GM dramatically improved survival during heavy loads and high temperatures. The result was an engine that remained remarkably forgiving. Miss an oil change? It might survive. Tow beyond the recommended rating? It would probably survive. Drive across the country with 250,000 miles on the odometer? Chances are it would survive that too. Engineers had built-in margins that protected owners from their own mistakes. That's rare. Most modern engines are optimized so tightly that any deviation from perfect maintenance causes problems. The 5.3 was different. It tolerated abuse that would destroy other engines. And then the real test began. America's truck market exploded during the 2000s. Millions of Silverados, Tahoes, Suburbans, Avalanches, Yukons, and Sierras left dealerships with 5.3 Vortecs under the hood. Production numbers climbed into the millions. The engine became one of the most common V8s ever produced. GM installed it in half-ton trucks, SUVs, and commercial vehicles. It became the default choice for countless buyers who just wanted reliable transportation. Normally, massive production exposes weaknesses. Weak engines earn bad reputations quickly. The 5.3 earned the opposite. Stories started spreading. A ranch truck in Montana with 450,000 miles still running its original short block. The owner had replaced the water pump twice and the alternator once. Otherwise, just oil changes. A contractor's Silverado crossing 500,000 miles hauling tools and materials across Texas. The odometer had rolled over once already. The truck had been in 3 accidents. The engine never missed a beat. Fleet vehicles surviving decades of abuse. Taxi services in some cities ran Suburbans with 5.3s past 400,000 miles before retiring them. Airport shuttles accumulated incredible mileage. Delivery companies depended on them. Of course, no engine is perfect. The 5.3 had its flaws. Intake manifold gaskets occasionally failed on some early variants. The gasket material would degrade over time, causing coolant leaks. It was annoying but not catastrophic. A competent mechanic could replace the gaskets in an afternoon. NOx sensors could become problematic. They would fail and trigger check engine lights. The engine would run in reduced power mode. Again, annoying, but not a fundamental failure. Water pumps eventually wore out. Fuel pumps sometimes failed. Thermostats stuck. Ignition coils occasionally died, but these weren't catastrophic bottom-end failures. The core engine itself remained incredibly resilient. That's an important distinction. Many engines fail because their fundamental architecture is weak. Crankshafts break, blocks crack, bearings spin. When that happens, the engine is often scrap. Repair costs exceed the vehicle's value. The 5.3's architecture was exceptionally strong. When components failed, they were usually accessories or external parts. The actual rotating assembly, the block, the heads, the fundamental structure kept functioning. Owners could replace a failed sensor or pump and drive another 100,000 miles. And then Chevrolet made it even better. In 2005, GM introduced the Gen 4 versions. Engines like the LH6, LC9, and later variants incorporated improvements in efficiency and emissions. Aluminum block versions appeared in certain applications. Electronic controls became more sophisticated. Variable valve timing was introduced on some versions. Horsepower climbed. By the late 2000s, many 5.3 variants produced between 315 and 320 horsepower, with torque figures approaching 340 pound-feet. The engine was growing. Technology that had been reserved for performance engines migrated into the workhorse 5.3. Customers got better fuel economy, more power, and cleaner emissions. Yet reliability remained impressive. The basic formula hadn't changed. Strong block, strong crankshaft, strong bottom end, reasonable operating speeds, conservative tuning. That's a recipe for longevity. GM's engineers understood something fundamental. You can add technology to a solid foundation. You can't add a solid foundation to technology that's already built on weakness. But then something happened that threatened the engine's reputation. Active fuel management. AFM, introduced on certain Gen 4 engines, could deactivate 4 cylinders during light load cruising. In theory, it improved fuel economy. Sensors monitored driving conditions. When the computer determined full power wasn't needed, solenoids would deactivate 4 cylinders. The truck would run on 4 cylinders like a more efficient engine. In practice, results were mixed. Some owners experienced excessive oil consumption. Others encountered lifter failures related to the cylinder deactivation system. The system added complexity. More complexity meant more potential failure points. The failures weren't universal. Many AFM-equipped engines ran for years without issues. Millions of trucks with the system never had problems, but enough failures occurred that online forums filled with complaints. Mechanics developed procedures to disable the system. What makes this interesting is what happened next. Even when AFM components failed, many engines still survived. Owners often repaired or removed the problematic systems and continued driving for another 100,000 or 200,000 miles. The AFM system might have failed, but the engine underneath was still fundamentally sound. The underlying engine architecture remained remarkably durable. That says a lot about the original design. Meanwhile, competitors struggled. Ford's early 5.4 Triton earned a reputation for spark plug and timing chain issues. The spark plugs could break off during removal, leaving pieces embedded in the cylinder head. Expensive repairs followed. Timing chains stretched, causing noise and eventually engine damage. Some overhead cam truck engines became expensive to service as they aged. Repair costs climbed. Complicated valve trains required specialized tools. Labor times increased. The Chevrolet 5.3 remained relatively simple. Push rods, 2 valves per cylinder, compact dimensions, easy access to many components. A shade tree mechanic could still work on it. Parts were affordable. Procedures were straightforward. That simplicity mattered to owners who needed to keep trucks running on tight budgets. Less complexity often means fewer opportunities for failure, and truck owners noticed. By the 2010s, used vehicle buyers actively searched for 5.3 powered trucks. Not because they were flashy, because they were dependable. A Silverado with 180,000 miles wasn't necessarily considered worn out. Buyers knew that if the truck had been maintained reasonably well, the engine probably had another 100,000 miles left easily. For many buyers, it was barely broken in. The aftermarket noticed too. Performance tuners discovered the engine's incredible strength. Stock bottom ends routinely handled significant power increases. Turbocharged builds began producing 500, 600, even 700 horsepower. Guys were bolting on superchargers and adding massive amounts of boost. The engines absorbed punishment that would grenade other designs. Some racers pushed far beyond that. Drag racers built 100 Euro horsepower versions. The same basic architecture that powered millions of work trucks also powered 9-second quarter-mile vehicles. With upgraded internals, the engine's potential seemed almost limitless. The deep skirt block and robust crankshaft architecture kept proving themselves. One reason is geometry. The 3.62-inch stroke wasn't excessively long. Piston speeds remained reasonable. Rod angles stayed favorable. Internal stresses were well controlled. The bore and stroke relationship was nearly square, which balanced breathing efficiency with mechanical stress. The design left a large safety margin. That's exactly what you want in a work truck engine. Most people think durability comes from making parts bigger. That's only part of the story. Real durability comes from balance. Every component in the 5.3 was matched to realistic operating conditions. The pistons were designed for the compression ratio and cylinder pressures they would actually see. The connecting rods were sized for the forces they would actually experience. The valvetrain was engineered for the RPM range the engine would actually use. The pistons weren't exotic. The connecting rods weren't race car parts. The camshaft wasn't aggressive. Everything was designed to work together for hundreds of thousands of miles. And it worked. By the mid-2010s, stories of 300,000-mile 5.3 trucks had become common. By 400,000 miles, nobody was surprised anymore. Online forums dedicated to high-mileage trucks featured dozens of examples. Facebook groups shared photos of odometers showing ridiculous numbers. Some fleet operators reported engines lasting longer than transmissions, differentials, suspension components, and even vehicle bodies. The engines simply refused to quit. Then came the next generation. Direct injection arrived. Variable valve timing became standard. Power climbed further. The newest versions benefited from decades of refinement and modern technology. Newer versions pushed well beyond 350 horsepower. Technology increased. Complexity increased. Yet the DNA remained the same. Strong foundation first, everything else second. That's the hidden truth behind the 5.3 Vortec's success. It wasn't magic, it wasn't luck, it wasn't marketing, it was engineering discipline. GM engineers resisted the temptation to chase headline numbers. They built an engine that delivered enough power while preserving enormous durability margins. They understood their customers needed engines that worked, not engines that impressed magazine reviewers. That decision paid off for millions of owners. Today, original LM7-powered trucks from the early 2000s are still hauling trailers, towing boats, and commuting to work. Many have odometers that would have sent lesser engines to the scrapyard years ago. They're not museum pieces. They're working vehicles, still earning their keep. Some have crossed 500,000 miles. A few have gone even farther. And that's why the 5.3 Vortec became a legend. Not because it was the fastest, not because it was the most powerful, but because it kept showing up for work long after everyone expected it to be dead. In an industry obsessed with horsepower numbers and marketing hype, Chevrolet accidentally created something far more impressive, an engine that earned trust. Trust isn't given freely. It's earned through years of consistent performance, through delivering on promises, through simply working when it needs to work. That's why mechanics respect it. That's why truck owners swear by it. And that's why, more than 2 decades after its introduction, the 5.3 Vortec remains one of the most beloved truck engines in American history. If you enjoyed this story, let me know in the comments which legendary truck engine you want to see next. And make sure to subscribe for more deep dives into the machines, engineering breakthroughs, and forgotten battles that shaped automotive history.